Hey everybody, today we're going to talk about the concept of centripetal acceleration and eventually the forces that cause centripetal acceleration. First, a reminder, acceleration is a change in velocity, and velocity has both a speed and a direction. So far this year, all we've really been talking about is a change in speed, either an acceleration or what we sometimes call a deceleration, which is a negative acceleration. Now we're going to be talking about centripetal acceleration, which is a change in direction. The speed will probably stay the same, but it won't be going straight, it'll be turning. Now, first, a couple properties about centripetal acceleration. Centripetal acceleration does technically have a direction. It changes the velocity towards the center of what's usually a circular path. Centripetal acceleration also has a number, a magnitude associated with it, and that is given by the formula here. The centripetal acceleration is equal to the speed, the actual magnitude of the velocity, squared, divided by the radius. If you were to imagine that object continuing to turn in a full circle, what would the radius of that circle be? Centripetal acceleration also has units, and they're the same units that we have for regular linear acceleration. So the standard unit for that would be meters per second squared, or in the English system, it would be feet per second squared. And typically, a very common unit for centripetal acceleration to be measured in is in terms of g's, and that is multiples of gravity. So 1 g is equivalent to 9.8 meters per second squared, or equivalently 32 feet per second squared. That can be a conversion factor that you can use in problems. So here's an example problem. The cars in the Indianapolis 500 travel around at over 200 miles per hour around the curves, and each curve is a quarter-mile long 90-degree turn. And I want to calculate what is the centripetal acceleration on the cars and the drivers. What do they experience? How many g's is it? So, to measure centripetal acceleration, we will need a velocity, how fast the cars are moving, and square that, and then divide it by a radius. So, we have a velocity, we'll say 200 miles per hour, and but it's not in a standard unit. So we'll start with 200 miles per hour, and I remember a fact from earlier in the year that 60 miles per hour is equivalent to 88 feet per second. I think maybe we used that in one of our videos, or maybe it's just a fact. I don't remember. But anyway, that conversion can be done pretty quickly, and 200 miles per hour is pretty close to 300. My calculator gave me 293 feet per second. So almost a football field every second is how fast these guys drive by. And I need to figure out what the radius is. I do know a little bit about the turns. They are quarter-mile long, and that covers a rotation of 90 degrees, and I need to figure out what the radius is. We can use some unit conversions to calculate this, or you could draw the whole circumference somehow and find it. I'm going to use the unit conversion just to show you one more example of that. I'm going to start with 1/4 mile is, or 1/4 mile per 90 degrees. And what I'd like to do is to figure out how big 1 radian is, convert my degrees to radians, because remember that a radian and a radius can be interchanged. So if I can find this, how many miles a radian is, or maybe better, how many feet a radian is, that will get me my radius. So that's an easy conversion to go from degrees to radians. There's 180 degrees in pi radians. And if I quit right now, I would have miles per radius. But I'd like to have my radius in feet probably. So we'll just do one more quick conversion. 1 mile and 5,280 feet are equivalent. So miles cancels, degrees cancel, and I have how many feet per radius, or radian, but so many feet per radius. When I calculated that out earlier, it was 840 feet. That's my radius. So to find the acceleration, the formula is v squared over r. So I will put in our velocity, which is 293 feet per second. That number is squared. And divide that by the radius, which is 840 feet. And when I calculate that, 293 squared divided by 840, I get 102. And the units for this, since it's feet per second, and really this unit is squared, feet per second, divided by feet, one of the feets cancels out, so I'm left with feet. And I've got per second, or feet per second squared. So that's a standard unit for acceleration. What would be interesting to know, I think, would be how many G's this driver is experiencing. And to do that, I'll do a quick conversion. And 102 feet per second, if I multiply that by 1 G, which is equivalent to 32 feet per second squared. So essentially divide 102 by 32. We get approximately 3 G's. Centripetal accelerations, or turnings, are always caused by some sort of an imbalance of forces, a net force that acts inwards towards the center. And the more mass an object has, the more force that would be required to change its direction. And that's just essentially Newton's second law, which says that the force required to cause acceleration is equal to the mass times the acceleration desired. And so if we replace the A, in this case, with a specific type of acceleration, centripetal acceleration, then we get that the centripetal force, or the force required to turn something, is simply equal to m times v squared over the radius. And that is the force required to cause the turn. So, a handful of examples. The first example is a centrifuge. A centrifuge is spinning, and it spins in a circle that has a radius of 18 centimeters. And it spins around 11 times per second. And I'd like to calculate what is the force that's exerted on a 1 gram particle that might be in that tube. So to calculate the force that's required, this object is definitely moving in a circle at a constant speed, and so we can use the formula that the force that's acting on the particle is equal to m, the mass of the particle, times its velocity squared divided by r. And when I plug in numbers for this, I will have to make sure that I use the standard unit each time, so that my force comes out in a standard unit of newtons. The mass is given to us in grams, and the standard unit is kilograms. So 1 gram is equivalent to 0.001 kilograms. And the velocity was not given to us directly, but we can calculate it. We do know the rotational velocity is 11 revolutions per second. And I'd like to convert that into a linear velocity, which is going to require that we use the radians conversion we've done before. So 1 revolution is equivalent to 2 pi radians. And I was told the radius is 18 centimeters. So I can write 18 centimeters per radius. And so now I know the speed that the gram particle is moving in centimeters per second, but the standard unit is meters per second. So I'll do one more conversion and go from centimeters into meters. When I did this calculation earlier, I got that the particle was moving at 12.4 meters per second. So I'll write in up here 12.4 squared. And then the radius is 18 centimeters, and that's not in a standard unit. The standard unit is meters. 18 centimeters divided by 100 is 0.18 meters. And so I can calculate this. It gives us a force of 0.068 newtons. Since everything was a standard unit, I get a standard unit of force out. And that doesn't sound like a whole lot, but 0.068 newtons for a 1 gram particle. A gram is tiny. 0.068 newtons is actually quite significant. Here's another question. A car is going around a curve at a certain speed, and we want to know what coefficient of friction is required to keep that car from slipping. And so if it's icy, then the coefficient of friction might not be high enough. Maybe we won't be able to make the turn. So to answer a question like this, it's a good idea to draw a force diagram first so we get an idea of what is the force that's causing the turn. And so for a car on the road, it is got weight that's pulling it down, and it has a normal force which is holding it up. And as it's making the turn, the force that's causing it to turn is the friction between the car's tires and the road. There is no force that is acting against that friction. A lot of you might think there's some sort of force that keeps the car going straight. There isn't one. It would naturally want to go straight because of momentum, and friction is trying to turn that momentum around and change its direction. And so the weight and the normal force, they'd have to balance. So that's an equation we can write. And the other equation that we can write is the fact that these side-to-side forces are unbalanced. So the net force is equal to friction. Then we also remember from our last slide that the net force has to equal the centripetal force formula. Since friction is equal to F net and F net is equal to centripetal force, I think we can combine those equations and create a good starting point that the centripetal force is equal to the force of friction. And now if we start to use some of the formulas that we have, the centripetal force that's required to cause an object to turn is the mass of the object times the velocity it wants to turn at squared divided by r. And then the formula for the friction that's acting on this car in this case is mu times the normal force. In this example, the normal force is exactly equal to the weight. So mu times weight. And the formula for weight is mg. So overall we have mv squared over r is equal to the coefficient of friction times mass times gravity. And I see something kind of interesting here. The mass is on both sides. This is the mass of the car that's going around in a circle, and this is the mass of the car that's helping to create the friction. And so we can divide both sides by m, or essentially cancel it out. We almost have mu, a quick division by g, which is the same as putting g in the denominator of this fraction. And we've got a very useful formula here for any object that is moving around in a circle, turning due to friction, and it's the only force that helps cause its turning. Well, then the coefficient of friction would have to be equal to v squared over gr. if we want to answer this question, I think we can start plugging in some numbers. And the velocity for this problem was 61 feet per second squared. So 61 squared on top. That was in feet per second. And so if we use the standard unit of g in feet per second squared, that's 32. And the radius in this problem was 130 feet. The weight of the car, 5,200 pounds, doesn't come into play at all because earlier you saw that mass canceled out. And so this calculation is simple enough to do. 61 squared divided by 32 divided by 130 gives us a coefficient of 0.89 would be required. If we want to travel around this curve any faster, then v squared would be higher and our coefficient of friction required would be higher. So that's why one of the things you have to do when you go around the curve is to slow down. Or if we wanted to turn any sharper, a sharper turn, what that means is that your radius would be smaller. And if you wanted to make a sharper turn, well, again, you would need a higher amount of mu. Thanks for listening, and be sure to tune in again later for some more videos on centripetal forces and specifically how they cause big planets and satellites to go around the Earth in very predictable patterns.